Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Green Tech Today is provided by Cachefly at CACHEFLY.com.
This is Green Tech Today, the Twit Network's Top 25 Green Tech Innovators Series. This episode of Green Tech Today is brought to you by the Eco-Imagination Challenge from GE. GE and its partners are awarding $200 million to ideas that help build the next generation power grid for the 21st century. For more information and to view and comment on ideas, go to ecoimagination.com/challenge. Potholes are normally considered a nuisance, but a Boston, Massachusetts company called the Levant Power Corporation is turning bumps in the road into electricity for vehicles. By harvesting the energy normally lost as heat by the suspension system, their GeoShock shock absorbers not only increase vehicle fuel efficiency, but also ride quality. We're in Boston, Massachusetts, and I'm at Levant Power, where they're getting power from vibrations. I'm with David Diamond, the Vice President of Business Development. David, tell us about what you're doing, what you're designing here.
Well, a number of years ago, a couple of undergraduate students at MIT were interning out on the West Coast, and they were driving in a car together trying to figure out how they could start a company. And they kept going over bumps, and they said to one another, my gosh, there's got to be a ton of energy in these bumps that we're hitting. How could we capture it? So they came back to MIT, and while they were undergrads, they put together a shock absorber with Home Depot plumbing components, and they came up with this idea of using the energy from bumps in the road to spin a motor that would spin a generator and generate electricity. So the idea is that we will put these in a wide variety of vehicles and derive some advantages from this. The obvious advantage is the ability to use the electricity. The less obvious is that we have an ability to be both softer and stiffer than traditional shock absorbers.
Is there more control going in, like computer control systems that are going into your shocks?
For sure. There's a whole control algorithm, and there's a whole series of refinements that we're actually engaged in performing right now. For passenger cars, you know, our rear ends are much more sensitive than you'd expect. You can feel when the curve of a shock absorber isn't smooth. So a lot of our initial work is focused on very heavy vehicles where a lot of that sensitivity isn't as great a concern.
Okay. Now, how is your shock absorber different from the standard shock absorber? What are you doing that makes it unique?
So a traditional shock absorber is the cylinder filled with oil, and you push a piston through the oil, and there's a hole in the piston. And if the hole is small, the piston moves slowly and with a lot of force, and that kind of slows the wheel down so you don't bounce over bumps as aggressively. And if the hole's large, there's very little force and the piston moves rapidly. A lot of the semi-active shock absorbers that you find on higher-end vehicles today have a mechanism for changing the size of that orifice.
Okay.
A valve that moves out of the way, or a hole that gets larger, or actually the oil that might change viscosity. We do something entirely different. We force that oil to do work. We push it through a hydraulic pump that spins. There's an electric motor attached to that pump. Mm-hmm. And we pull energy off of that shock absorber as you're driving down the road.
Okay. There seems to be, are there a lot more parts, working parts, in your shock absorber?
We thought there would be, but actually, as we disassembled traditional shocks, we were able to eliminate a number of components that were in a traditional shock. So the parts count is actually not that different from a traditional shock absorber. So we're pretty confident that we're going to be able to deliver a shock absorber that's cost-effective as well as effective in its intended use.
Okay, and what are the intended uses? So you mentioned military, heavier vehicles.
Well, there's three variables that really come into play when you're trying to figure out how much energy you might be able to recover from the road and from a shock absorber. The mass of the vehicle, the speed of the vehicle, and the surface roughness it's traveling over. Military vehicles are spectacular. They're 30 tons, they're driving over logs and trees and trying to go fast. So there's a lot of energy to capture there. Similar vehicles would be long-haul trucks, city buses, believe it or not, drive over a moonscape through our major cities.
Right.
And rail cars, believe it or not, they don't actually move up and down so much, but if anyone's ever been on a train, you get this tremendous side-to-side motion.
Right.
And they're 100,000-pound cars, so there's a lot of energy to capture there. We see this technology being applied to anything that moves.
Okay, are you looking at electric vehicles? I mean, there's a huge work going on there for efficiency and capturing as much energy as they can to maintain the battery life as long as possible.
For sure, and that's a great use of this technology. The lighter the vehicle, the less energy we produce,
Right.
but we do present a trickle charge to a lithium-ion battery pack. Lithium-ion likes to be trickle charged. It extends its life, and lithium-ion hates to be discharged deeply. So they don't like to go down to 0% charge. So by having something that provides this constant charge, we can help those battery packs.
All right. So weight concerns, are your shocks significantly heavier, or?
They are heavier. There's a little bit more material inside for this integrated piston head, as we call it, all the mechanics. We don't expect to be more than 1 kilogram heavier than a traditional shock, so we don't think there's going to be a weight penalty. There is a secondary controller that's also several kilograms, but I think as we get into production, those weights will come down, and in fact we'll probably end up using other computers on board the vehicle to control various aspects of the shock's performance.
Right, so the shock doesn't necessarily, the control systems don't have to worry about everything. They'll be more a working part of the vehicle.
Yeah.
So how are you looking at developing this business? What are the challenges that you're up against in getting adoption?
I don't think we're finding any lack of interest. When we call, we're fortunate we get calls back from most of the major automakers and tier 1 suppliers. Our challenge is just blocking and tackling. We just went through this past weekend building a first set of our 5th generation prototype, which a team is delivering to customers in Detroit this morning. And the challenge really is going to be to prove we can do the things that we say we can do. We can improve safety and ride and handling and performance, all the while generating energy in a shock that lasts. Nobody wants something that's attractive, that doesn't endure.
Right, you need this to be reliable.
Yeah.
Yeah, and sometimes with more moving parts, with finer computer equipment, sometimes something especially like a shock that's undergoing a lot of movement and a lot of, I guess, a lot of pounding over time, parts probably wear down. And so how do you keep that reliability up?
There are a number of things that we do, and we're really fortunate because what we're doing is taking energy out of a traditional shock absorber that would otherwise be wasted as heat.
Right.
And that heat degrades the seals, it degrades the fluids. So a traditional shock we expect will actually not last as long as GeoShock. We think our shocks are going to be more durable, more reliable. And because we can accommodate wear, so your shock today, you drive 100,000 miles, on day 752, the shock isn't going to feel like it did on day 1.
Right.
Our shock has the ability to adjust itself as it ages, because we can control that motor and control how much force we're providing. So on the last day of service, our shock should feel just the same as it did on the first day of service.
That's a good selling point.
Yeah, we're kind of excited about that.
So do you want to show us around here and tell us what you're
Sure.
what you're doing and how you're developing?
Sure. So basically we tried to set up a flow, even though we're not a high rate production facility here, and we bring our materials in. We generally start here on one of the larger lathes. We have tube stock that forms the pressure tube for the shock absorber, and we cut those to length. We come around and we have a second lathe that allows us to mill various features in some of the components, and we carefully removed the sensitive components
Right.
so they wouldn't be exposed to this production. But we can mill all sorts of different shapes in our integrated piston head to manage fluid flow, to ensure that we're channeling that oil past our hydraulic pump in a way that allows us to control it efficiently. And then we go off to our next room, which is the dyno room.
Okay.
And there we assemble our units and put these systems on a dynamometer.
So you can actually test how they're working under load.
Exactly. A dynamometer takes inputs from a computer and will replicate what a shock absorber might see on the road. So this dynamometer here happens to be a tabletop unit, and it will pump this shock absorber up and down at a prescribed rate. And as it does that, we measure its temperature. So there's a temperature sensor here. So we watch the buildup of temperature. And we also measure the power output. This isn't trimmed for road use. This is trimmed for this dynamometer. So the wires come out directly, and we can attach them to a variety of different devices to measure their performance.
Okay. Well, hopefully we can get a look at that.
Sounds good. Let's see if we can get Clive to show us how this works.
Okay.
We're partnering with 4 of the biggest venture capital firms in the clean energy space, 3 in the US, 1 in Europe. Again, we think that the combination of GE investment and venture capital investment is going to allow us to increase innovation. It's going to allow us to accelerate new ideas. It puts us shoulder to shoulder with some of the smartest tech investors, and we can use what I would call the industrial clout of GE to bring technologies to this marketplace faster.
GE announced its challenge at a San Francisco event along with its 4 venture capital partners. Emerald Technology Ventures, Foundation Capital, Kleiner Perkins Caulfield and Byers, and Rockport Capital Partners have all joined with GE. Ideas from companies and individuals can be entered through the ecoimagination.com website for the next 10 weeks. So check out ecoimagination.com.
We're back, and we're going to see how GeoShock, Levant Power's shock absorber, works. We've got it hooked up to a dynamo. I'm with Clive Tucker, Chief Design Engineer. Can you tell me a little bit about what your setup is here and what we're going to see?
Sure, absolutely. This black box is the dynamometer itself. It will drive the bottom of the shock absorber up and down. The top of the shock absorber is fixed. This is our GeoShock itself, in between the top and bottom mounting. And as the shock absorber goes up and down, of course, we pass fluid from one side of the piston to the other side, as you do in a conventional shock absorber. But instead of just wasting that energy that's in there through orifices, we actually capture that energy via a hydraulic unit and an electrical generator. That's all housed inside of the body. We have our connections coming out through the fixed top of the shock absorber. And that's going right now just to power some lights to show the electricity that's being generated.
Okay, so when you turn this on, we should be able to see that there is power coming out, because we'll see the lights start turning on.
Okay.
Start test.
Okay.
So I noticed that the lights were flashing on and off. What does that indicate?
Basically, as the shock absorber goes through its motion, it starts off at 0 velocity, and halfway through its stroke, it reaches maximum velocity. When it reaches the top, it goes to 0 again, and obviously the same on the way down.
Okay.
And the amount of energy that we produce is proportional to the speed of the shock absorber. So that's why at the top and bottom, you'll see the lights go dim. When you're at the mid-stroke, the lights are flashing brightest, and then again they go off again at the top. And when you come back down, then they go bright again in the same exact same manner. So power you're getting out of it is very cyclic, and it all depends on how big the bump you're going over, how fast you're going over the bump, all depends on how much energy you take out. So obviously that's a very erratic output. So what we do, we put that into a big fancy control box with a lot of electronics that takes all that erratic power and sends it out as a nice uniform current that the vehicle can use in whatever terms of voltage and power that the each application requires.
Right, so is it like a capacitor or a battery in that sense?
There's capacitors.
Not a battery itself.
Yeah, there's capacitors and a whole bunch of electronics in there. I don't know that. I'm the mechanical guy, not the electrical guy. But, yeah.
How much power are you getting out of this, max power?
Out of this one unit, about 1.4 kilowatts.
Okay.
But this is designed for a sort of a pretty heavy-duty vehicle, military vehicle. So depending upon the application, you can be anywhere between a few hundred watts up to several kilowatts, depending upon the application.
Okay, so there's a broad range of how much energy you're actually going to get out of it.
Exactly. Yep.
Right.
Yeah.
What conditions would this be optimal under? Where do you see it working most optimally?
Well, basically, for right now, for military vehicles, that is the optimum vehicle because they tend to be very heavy. And they tend to go over a lot of rough terrain. If you're out in Afghanistan or something where the roads are in terrible condition, you're going over big potholes and things like that, rocks, and you're going off-road, then you get in a lot of motion, a lot of speed, and with a heavy vehicle. That equates to a lot of damping, that equates to a lot of power output. Okay. The lower end of the scale will be passenger cars. They tend to be a lot lighter, the roads are a lot smoother, or sometimes they tend to be smoother. And then you have also things like Class 8 trucks, again on smooth roads, but there again you're dealing with a lot of mass of the vehicle, so that also gives you significant energy.
What kind of concerns did you have to deal with when you were designing this shock absorber?
Well, basically trying to package everything inside of the shock absorber.
Yeah.
As you say before, the previous prototypes where everything was external. You got a lot more space to deal with, but it's not elegant and very inefficient. So the idea is to take all of that external components, put it inside a package that is durable, also fits within the standard shock absorber dimensions. Because the idea being that this will be a retrofit. You take off the existing OEM shock absorber and fit this one on. So it can't be much bigger, or you've got to have the same stroke and the same damping forces.
Right. You
so
don't want people to have to go out and buy new parts to be able to add your shocks to their vehicle.
Exactly. Yep.
Yeah.
And they want to have the exact same ride characteristics and everything, just with the bonus of capturing power. So trying to fit all of those components in a durable package, because obviously the life of a shock absorber is pretty tough. It's forever just getting hammered.
Yeah.
And it's got, especially in the military application, you've got to undergo rigorous tests. So trying to get something that's packages well and durable and produces the efficiency that we need is tough.
At what stage of evolution is this shock here? Is this the most recent shock you have?
This is absolutely, yes. This is our very latest technology. And it's encompassing all the lessons learned from Alpha 1 right up to Beta 2. Each step, getting incrementally better. But even Beta 2 was a good performance, but it didn't have the durability, and it wasn't really designed for any specific application. So basically, we took a lot of the lessons learned, but incorporated a lot of new technology as well to actually make this a durable shock absorber, something that we can pass on to our customers and have them test and be confident that it's going to pass, all their requirements.
Yeah. What kind of technology is necessary for durability in a shock absorber?
Well,
like what kind of recent advances have really made this, possible?
Basically, a lot of the newer motor technology allows the motor to be to harness more power from a smaller package. Okay. And also some bearing technology that we have inside of it, because we've got a lot of spinning components that are forever going one way, stopping it going back the other way. A lot of accelerations and decelerations going on. So in order to make a package that can withstand that, required some...
Not throw a ball bearing every couple of hours.
Exactly, that's right. Yep. So it required some good bearing technology, to handle those kind of forces and speeds. And then basically making sure that the quality of all the parts that we have are up to spec. We've done a lot of research in inquiring what kind of materials are required, what kind of surface finishes and hardnesses and tolerances we require, and then making sure that our suppliers actually met all those requirements.
What are you excited about moving forward? I mean, this is not the end of the evolution of the GeoShock.
This is basically just the start.
Right.
Exactly.
What things excite you about it and where it might go?
The number of applications, I mean, it's almost an infinite number of applications. Anything that moves right now, that we can put a shock absorber on, we can capture energy from.
Yeah.
So everything from, as Dave was saying, from bicycles up to large buildings. I mean, certainly in a lot of areas they have big dampers on top of skyscrapers to lessen the motion that's going on, but also for earthquake, survivability. We can have GenShocks there. We can have GenShocks on bridges, trains, and also you're talking about the ocean gen. So we can capture energy where there was, previously not possible. And right now, that's a hot ticket, capturing energy. So that makes it exciting, and it's a challenge. Trying to fit everything in there and make everything work. And it's, as an engineer, that's fun. We enjoy doing that kind of thing. So.
Right, kind of the ultimate job, getting to do what you love and have it be something that is a challenge.
Exactly, and it's a worthwhile product.
Yep.
That's a good thing. We're definitely making a difference.
Great. Well, thank you very much.
You're welcome.
So, David, you mentioned how the evolution of this product has occurred. It started in a dorm room. Notice you've got all this stuff up on the wall, kind of documenting the history. Can you take us through it?
Yeah, this is our museum. So we call this the pizza-powered GenShock unit because over pizza in a dorm room and Home Depot components, Zachary and Shaquille, our two founders, created this. They used this to win the MIT business plan competition, which came with a $100,000 award.
That's a nice award.
It also introduced them to people that would be interested in GenShock, and one of them happened to be a defense contractor who produced our first commercial contract. And for that, we made the Alpha 2.
Okay.
And basically, what we did was we wanted to be able to prove we could deliver damping and simultaneous production of energy, which this fulfilled. But its efficiency wasn't terrific because there's a lot of loss in these long tubes and pipes and devices and things. So the idea was, well, if we're losing energy in these pipes, let's see if we can consolidate it all into a very small package.
Right.
And that led us to the Beta 1. And this integrated piston head is really the...
Can we take it off the wall?
We can.
Look at it?
We can. This is one of the earliest examples of the integrated piston head. These were flow paths for the fluid to enter a chamber. We forced the fluid to go past the hydraulic motor here, and without getting into too much more detail, that allows us to generate some energy.
It's pretty amazing that you went from, this jump from Alpha 2 to Beta 1 is a really substantial change in the design.
It's a lot of intellectual property that's associated with that step. We think we have probably the world's best design for this type of shock absorber, and we're very excited about the design because it lends itself to so many different applications. Once it's small, you can scale. You can scale it down, you can scale it up, and it's elegant, it's convenient. And what we did from Beta 1 to Beta 2 was simply look at efficiency, look at noise, look at limited durability so that we could, last long enough to show that we can do the things we say we can do. And ultimately that led us to our 5th generation, which Clive showed us.
Right, which is the current generation. But from Beta 1 to Beta 2, what were the differences here? Just
primarily efficiency. So we looked at the shape of the components we were selecting. We looked at the fluid paths. Fluid is a lot like human beings. It doesn't like to take sharp corners.
Right.
It likes to go from point A to point B in the straightest path possible. So we looked at things like that inside of the shock. And quite frankly, that's what Clive brought to us for our Beta 3 shock. I was describing to you earlier that I think it's elegant because there are many, many small, medium, and large changes that make the unit perform better.
Great. And are you looking forward to seeing it evolve further into the future? I mean, it's elegant now, but where do you see it?
I think the pinnacle of GenShock development will be when nobody thinks of it, when it's just an afterthought. Well, of course you have energy-producing shock absorbers on your car. Well, why would you waste that energy? And that'll be when we know we've made it. And the excitement of bringing the technology to many, many different markets, to the ocean, to every vehicular market you can think of, to buildings and bridges. That's fun. There'll be so many opportunities for us to innovate and create. That'll be fun for a long time.
Sounds like it. Thank you very much.
Thanks.
So that's Levant Power. They're working on GenShock, the shock absorbers that might power our future. That's it for this episode of Green Tech Today. Subscribe at twit.tv/GTT and never miss a show. If you have a question or a comment, email us at greentechtoday@twit.tv. Or you can leave a voicemail at 415-GT-TODAY.